How's it going, guys? In this video we're going to go over enthalpy change, and we're going to continue on with the thermochemistry series here. And I'm going to kind of give a series of problems that, I'm going to give one type of problem and then a whole bunch of different questions that could be asked, just because I think it's useful to attack the problem from as many different angles as you possibly can, just to prepare, because a lot of times you see a different type of example that you've never seen before when you get the exam. So that's always rough if you're not prepared. So first off, what is enthalpy? Enthalpy is basically just heat change at a constant pressure, and that can be gain or loss. But just remember that if the delta H, or the enthalpy change, is greater than 0, it's endothermic, and if it's less than 0, it's going to be exothermic. And you can kind of just a quick refresher on this chart. If you're going this way, if you're going to the right, it's going to be endothermic. If you're going to the left, it's exo. So without further ado, let's just jump into one of these problems. I'll leave that up in the corner. So here we go. 1. Okay, so we have methane burns according to the equation. Then we have, let's see, CH4 gas plus 2 O2 gas. It's going to yield CO2 gas plus 2 H2O liquid. And then we'll say we're given delta H is equal to negative 890.3 kilojoules for this reaction. So let's kind of see where this takes us. Now for 1A, we'll ask what will be the enthalpy change when you burn, and we'll give an arbitrary amount of grams. When you burn, say, 12 grams of CH4. So we're kind of taking some principles from Gen Chem 1, and we're going to apply that here a little bit. So basically what we're going to have is, let's just start off with what we're looking for. What will be the enthalpy change? Enthalpy change is going to be equal to, and then we'll just go with what we have. We're given 12 grams, and that's going to be of the CH4, but we don't need to write that. Whatever, I would as well, I guess, CH4. And then we'll go through 1 mole of CH4 is going to be that is going to be 16.01 grams of CH4. And then we'll just multiply that by that, because we'll multiply that by here, and this is going to be, well, I'll just do it and then I'll explain. 890.3 kilojoules per 1 mole of CH4. So basically what we've done here is we've taken this number here, which is the enthalpy change for this equation, and because of the fact that the methane has just a theoretical 1 here, compared to this, its molar ratio is just 1, or rather we're assuming there's 1 mole of CH4 with 2 moles of O2, just based on this. We can concur that the CH4, 1 mole of CH4 is going to have this effect. So if it was, say, like 2 moles or 3 moles or whatever, we're basically just trying to figure out how many moles, and we're going to do it that way. So we'll just multiply that across. That's going to be 12 times 890.3 negative is going to be, okay, and then that's divided by 16.01. We have negative 667.31 kilojoules. In this case, it's definitely relevant to include what's negative, what's positive. I mean, it really always is, but in this case, you know, it's pretty relevant, and we'll see why just in a moment. So that is going to be our answer here. We've just solved what will be the enthalpy change when you burn 12 grams. Okay, so we'll keep going from there. We'll just build off this same kind of formula here, because a lot of problems can be asked. These are really good, like multiple choice, open response questions that people can ask. So I guess things are all online, so it's probably going to be a lot of multiple choice, but okay, how much heat will be given off when you burn 8 grams of, I think, CH4. Okay, so this question is a little bit different. So basically, these are some keywords here: given off, and obviously you're burning it, because according to it, methane burns. So really, it's given off is what is the most significant thing here. Again, we're looking for the amount of heat that's given off. So what is the difference here? We have 8 grams, so we're starting out with what they give us of CH4. We'll go across. That's 1 mole of CH4 is equal to 16.01 grams. I'm sorry, it's not equal, but per. We're just setting up one of these. And then 0.3 kilojoules over 1 mole CH4 is going to equal. And so we'll just go across like this. So, and that's theoretically over 1, obviously. So we have 8 grams of CH4, and we're pretty much doing exactly what we did here. But there's a small difference. This is our calculation for the enthalpy change, and we're not going to take the change because it's just asking how much heat is given off. So essentially it would be like a Q from like one of these other ones, like the Q equals MCΔT. It's so basically with heat, we're going to quickly do that math here. Okay, so we got from this, I got 444.87 kilojoules. Rather negative because of this. Here's the problem. That works as a enthalpy change, but you're trying to find heat, and in this case, we can't have a negative heat. I think like some people might not actually care, but like if you want to have the technical right answer or whatever, you want to be able to defend. You know, there's no way you can be told you're wrong if you do for heat 444.87 kilojoules, and just leave it at that, because this is a heat. It's not a change, and this is just like how much heat. So there's your answer. And we'll just keep going from there, I guess. C, we'll say what will be the enthalpy change when you produce 21.0 liters of CO2 at 266 Kelvin and 740 millimeters of mercury. So this is going to be a really, I think, tricky problem if you're the type that only studies for the exact concept that you're learning. This is something that you're going to have to pull theoretically from Gen Chem 1, because you know you have a pressure here, and we're talking about thermochemistry and enthalpy changes, and why do you have a pressure? We'll just go back to the last most prominent time that we solved for these, PV equals nRT, and then solve for N, because eventually we're going to want to use, we're going to eventually want to get this into, it's asking for what will be the enthalpy change, and for enthalpy change we're going to want to use N. So we'll just rearrange this really quick. Do some quick algebra. We'll get solve for n, and n equals PV over RT. Easy. So now, let me see here. So we're going to just sub in all those numbers that we got. Let's say PV, we have our pressure, we have 740 millimeters of mercury. Then we have our V, which is thankfully in liters, 21 liters. And then we'll go down. We have our R, and in this case, hopefully, if depending on how long ago Gen Chem 1 is, they really should provide you with the R value. Here it's going to be 62.4 liters times mmHg over mole times Kelvin. I feel like that would kind of be a cheap shot if you had to have all those R values memorized. 266 Kelvin right there. And this kind of just worked out. We didn't really have to convert much. Let's see here, 740 times 21 divided by 62.4 equals divided by 266 equals. That's just the way I like to do it. I find I make fewer mistakes that way. 0.936 moles of CO2. Because why do we have moles? Well, let's cancel. We have the mmHg right here, mmHg. We have liters up top, liters right here. Then we have Kelvin on the bottom, Kelvin on the top, left with moles. And what are we looking for? Moles of carbon dioxide, so CO2. Now we have this, but that's not our final answer. What we've just calculated is, so what will be the enthalpy change when you produce this much CO2? Now we know how many moles of CO2. Let's figure out what the enthalpy change is that's going to result from that based on that formula all the way up there. So CH4 plus 2O2 yields CO2 plus 2H2O. So what we're going to do now is we'll take what we got, 0.936 moles of CO2, and we're just going to throw that in here. We're going to have negative 890.3 kilojoules, which we know we have based on what was given to us. We have the 890, the negative 890, and now this is all going to be divided by 2 moles, because unlike problem A, 1A, where we only had 1 mole and 1 mole, it kind of made it easy. Now we have 2 moles because there's going to be, oh no, wait. So we have CO2, CO2. I'm sorry, my bad. It will only be 1 mole because I thought we had 1. So we have 1 mole of CO2. Let's see, 1 mole of CO2 on that side. So we're going to keep going across. That will be, this is actually simpler than I thought it was. 0.936 times 890.3 negative. We're going to get negative 833.32, and that'll be in kilojoules because the only things we had canceled. And there we go. So we know now the enthalpy change based on the number of moles, which we figured out using PV equals nRT. Okay, so I think that was quite a confusing one for some people anyway. We're going to go into D, which will be the last one for this. How much heat will be released when you react 68 grams of O2. Now we're gonna get into the moles. So here we go. Just start with what they give us, 68 grams O2, and then we'll just go across we have 1 mole of O2 per 32.0 grams of O2 molar mass. And then we'll go 890.3 kilojoules. Technically that'll be negative based on what was given again right there. This time we look at the formula again. We have 2 moles of O2 based on what they've given us, so we're going to have 2 moles, and then we'll have something more to divide it by, and I believe that's it. We'll just figure that out. 68 times 890 divided by, okay, so we're going to have 945.94 kilojoules. So theoretically we'd have a positive times a negative divided by a smaller positive. We're going to end up with a negative number here. However, again, we're talking about heat, and like we set up here, heat can't be negative. So we're going to have technically 945.94 kilojoules positive is released. Or you could say that the change of negative 945.94, that's what it would have been. But yeah, it's asking what was released. That's your answer. Keep it simple, I think. And then we'll do just one more of these multi-part problems. I think they're worthwhile. You know, if you're really chasing that A, you want to be prepared for whatever way that they can rearrange these things. So we'll say when a 7.45 gram sample of NH4NO3 is dissolved in 800, let's see, I'll do 850 grams of water. The temperature drops from 28.0 degrees Celsius to 21.8 degrees Celsius, so not too big of a change. So we'll start off with A. Let's see, calculate the enthalpy in kilojoules per mole of NH4NO3 for the dissolution process NH4NO3 yields NH4 plus NO3 minus. So I think in a lot of these problems, if they're the most possible challenging type of problem and they really are going to rely on your chemistry background, they're not even going to give you the formula or the dissolution process, for example. They're just going to say, hey, here are the molecule, or here are the compounds, figure it out. And usually they're pretty straightforward. They won't give you something too crazy, but in this case they'll give us the water density, so we'll have 1.00 grams per ml, and then we'll give water, yeah, that's getting messy, water heat capacity equals 4.184 joules per grams times Kelvin. Okay, so we got a couple givens there. We got our formula. Let's break this down. So first of all, what are we looking for? Calculate the enthalpy. In this case, we can use this formula. Delta H is going to be equal to the negative heat over N. So if we're trying to figure that out, what are we figuring out? So N is going to be based on 7.45 grams that we know about. So we'll just figure that out. So what is N? N is going to be equal to 7.45 grams of NH4NO3 times 1 mole of NH4NO3. Shouldn't have picked such a long compound there. And then what is it? The molar mass I wrote out ahead of time, 80.0.52. Okay, grams of NH4NO3. There we go. Okay, so what do we got? Okay, so we got 0.0931 moles of NH4NO3. So now that we know our N, we can throw it right back into this formula here and then get a little bit closer, because what are we calculating? Calculate the enthalpy in kilojoules per mole. So here we go. Now we're going to say if we want this, we can find Q. We know Q equals MCΔT, which we can start to just throw things into our what's this going to be? So our mass is going to be 92.45 grams, and we'll have 4.184 joules times grams, and then we'll have, for our delta T, let's see, we have negative 6.2. And so we're going to have this right here, the 92.45. We're figuring out, because of the equation, basically we have the 85 grams and the 7.45 grams, and we're going to just put them together because it is together in this format here. 92.45 times 4.138 times negative 6.2. We're going to get negative 2398.23 joules. And then we'll take that, and remember the question asked for kilojoules. We'll just move that over. We'll get kilojoules. We'll use this formula here, right there. Delta H is going to equal, and this is going to be negative 2.40, we'll just round it, kilojoules divided by 0.0931 moles, and that way we'll get our kilojoules per mole. So obviously it's a negative, it's going to end up being a positive. We'll just do that. Okay, we're going to get 25.778, and that's going to be kilojoules per mole. And whatever, if you want to do sig figs, you can do 26.0 or whatever kilojoules per mole, depending. So that's pretty straightforward. We calculated the enthalpy in kilograms per mole of NH4NO3 for this reaction based on these numbers. So that's, again, kind of a slightly more unusual one, I think. We'll just do a couple more here, and then that'll be done. Okay, so this is a straightforward question, and I hope if you're comfortable with these, you get a lot of them, because I think that they're kind of like gimme questions. Is this process exothermic or endothermic? I guess this would kind of be unfortunate if you messed up on the previous problem. Now you're also going to make another mistake here, theoretically. But in this case, we have a positive. It's going to be endothermic, because it's endothermic if the delta H is greater than 0, which in this case it is. So we're good to go. Now C, we'll say, what would be the enthalpy change if you dissolved 3.26 grams of NH4NO3. On first read through, that at least last a year ago or something would have seemed pretty confusing to me, because how do you calculate if it's for dissolved? It says specifically for the dissolution process, which is just another way of saying basically the process of it dissolving in a way. And what we're given is grams. So let's see what we can use. I always like to start with what they give you and see where I can go from there. So 3.26 grams of NH4NO3 times, what do we got, 1 mole NH4NO3, and we did it up there. We're going to have 80.052 grams NH4NO3. Sorry, that's getting a little messy. Now, here is where we're going to do the next step. We have, based on what we have done previously, we can do, we have moles up here, we're going to need to get moles down here. 1 mole of NH4NO3. And what are we going to put up here? So what would be the enthalpy change if you dissolved this many grams? And we're figuring it out that way. What we're going to have here is 26.0 kilojoules. And that's going to come right from the problem A. Yep, that was A, where we were solving for the enthalpy in kg per kilojoules per mole of NH4NO3. So now we have that. We're going to borrow that number from what we already solved and go ahead. Again, this is being a multi-step problem. If you got that calculation incorrect, technically you could be using this. That would probably get you a little bit closer. We're going to have 1.06 kilojoules. And so what would be the enthalpy change if you dissolved? This would be all right, cool. So yeah, again, enthalpy, it's good to know. It's just heat change at a constant pressure. Keep that in mind. It won't always be the case in more advanced thermochemistry problems, but I think for most of Gen Chem it should be. And then if delta H is greater than 0, it's going to be endothermic. If delta H is less than 0, it's going to be exothermic. So yeah, a couple more problems here. Hopefully this helps someone.